Okay folks, almost time for our Thursday lecture. Let's get Microsoft Teams open somewhere. Organized. Just having a little think before pressing go about what demos I'm going to do today. That's a terrible demo, I'm not doing that one. I can't find one that I want to do. I might close that door. I think there's someone grinding outside. Just asking on the team whether if people have any ideas for demos or example code they'd like to see. I might have some time today, or I might have some time on Monday. I definitely will have time on Monday. So let me know what you'd like to see. Well, good morning to you. Welcome to COMP2300/6300 here on Thursday morning, Thursday of week 5, here in Canberra, streaming live. Thank you folks who are joining me online. I know I've got a small but committed group that likes to join me on Thursday mornings. I presume you've got a warm morning beverage in hand. You're either wrapped up in bed or wrapped up in the warm embrace of one of our flexible learning spaces on the ANU campus. And you've got all of your equipment around you ready to have a great day of learning about microbit stuff. Is that what we do in this course? There's probably a better way to phrase it than that, isn't there? So where are we today? Monday we had a marathon lecture looking at functions. And today we're going to continue that and start off at the bit we did partly on, some good stuff, okay. Partly on the area we left off, which was about the stack, which I'll need to keep going through. I might kind of restart and look at the whole of the stack section, so you just get that all in your brain today, and then we can keep going through the extra stuff, because there's a few more details about how the stack works, which are pretty important. Then the demo today, or the thing that I'd really like to do as a bit of worked example code, would be to make a recursive function in assembly. And the reason for that is that you need to use functions, and you really need to use the stack for a recursive function to work. You just can't do it unless you're using the stack. So we will need that, all of the capabilities we've learned this week in order to accomplish that task. So hopefully we get to that. I've just asked a question on the team, which is, if you have any idea for demos or example code you'd like to see, please ask me on Teams or by any means. And we have some time on Monday in week 6 to look at examples. I'm going to start my recording. That's a bit of a mistake. Welcome again. Sorry, I didn't start my recording before, so this is the second welcome to COMP2300/6300, week 5, continuing to talk about functions. And today we're going to do a deep dive on the stack, a dive all the way down to the base of the stack, or the head of the stack, because it's an upside down data structure, isn't it? What else should I mention? There's an assignment due next week. That's very important. If you don't know anything about the assignment, I don't know where you've been for the last 2 weeks. We've been talking about the assignment non-stop in labs. So many great questions, so many great ideas, great discussions with your tutor about your design proposals. But the important thing about the assignment is that it's a time-limited thing to do. It's really only a short project to make something interesting with the LEDs. So I know there's some people feeling very stressed about it, but you've had a period of time to work on a design document. Now's the time to sit down and try to make something happen with those LEDs and see if you're happy with it. And if you're happy with it, hand it in. You'll probably do fine. As long as you meet the specifications, you are making an engaging light show, something that is interesting to look at for 30 seconds and that it repeats endlessly, you should be fine. It's not an assignment which is designed to trip you up. It's probably one of these assignments which is devious in its simplicity, like it seems like there ought to be some trick. I don't know what the trick is supposed to be. You just make the lights do something cool, and then the more cool it is, the more work you have to do in your program to get it to do that. So you're demonstrating a more sophisticated understanding of the programming concepts we've been working on so far, and the knowledge of program execution. So of course there's ways to propose things which are probably way too hard. You can't do them in a whole week. I've seen a few design proposals which may be a bit ambitious, but the best way to find out if it's ambitious or not, after you've asked your tutor, had your discussion with them, and perhaps they've told you, the second best way is to just try it and see how far you get. So there's a weekend coming up. I say get your microbits out and have an exciting microbit light show time. And try not to get too stressed about the assessments. I know you've got other assessments for courses as well, but I'm just trying to give you a kind of a bit of encouragement that it's not something that you necessarily have to be stressed about. Hundreds of lines of setting LEDs, I know, but you've just copied and pasted them. Make some functions if you want to cut down your hundreds of lines. Make a function. There's a few suggestions about what to do. Someone's asked to look at how the circuit works for the lights. I mean, do you mean how it works with electricity, or do you mean how it works in assembly? Because I feel like the lab is a pretty good explanation of how to turn on a light in assembly. I guess it doesn't explain that much about the circuit. Is that what you want to know? Hundreds of lines of sending LEDs. Someone else has said, we learn more about assembly on the specific board. Yeah, I like talking about the board as well. I guess we're only just at the point where we can start to make sense of the board, because you're doing labs that start to use hardware stuff. We will do a bit more board related stuff at after the mid-semester break. Someone just says they want to know how the circuit works. Well, that's great. We can look at that for a minute before we get back to the stack. The microbit technical schematic, the PDF schematic for the microbit. Yeah, here's how the board works. So this is a typical kind of data circuit diagram thing. It's not really a diagram of the circuit. It's a diagram of the connections between the CPU or MCU on your microbit and all of the other stuff: speaker, microphone, buttons, touch sensing, motion sensor, LED matrix, expansion connector, etc. And this is the MCU, so it's got all of its different pins and input and output connections. And here's how the rows and columns for your LED matrix are wired up. So each col is one of those. Col 1, col 2, col 3, col 4, col 5. Those are one of the GPIO inputs or outputs. There's a few. Col 1 is this pin called PO.28. Usually on a microcontroller, pins have like several names, which is confusing, but the name within assembly that we're used to using is that one, port 0, pin 28. So each of the column lines is connected to 5 LEDs, and each of the row lines is connected to 5 LEDs. So this arrangement is called a matrix, right? Because it's like a 2D arrangement of these LEDs with rows across that are common. There's lots of things that use matrices. The keyboard in your computer uses a matrix for each key, just like my keyboard. Each key in a row will be one row, and each key in a column will be a column. Not sure if this one has 2 matrices, one for each side. I don't know. You could do it both ways. Matrices are really common in electrical engineering, electronics engineering, because you have a limited number of inputs on your device. So if you have a keyboard that has, mine has not that many keys, but you have a normal one that has around 60 keys, you may not have 60 pins on your microcontroller to have a dedicated pin for every single key on the keyboard. Same with the LED outputs. We've got 25 LEDs, but we don't want to use 25 pins to cover all of those LEDs. So we matrix them and have pins for rows and pins for columns. And you can see that the column pins have a resistor here. You always have to have a resistor in circuit with an LED, otherwise they draw too much current and burn themselves out. So the resistor makes sure that the LEDs don't burn so brightly that they go dark and never light again. I always forget what the orientation is. I'm not an electronics engineer really, so I forget what the positive and negative terminals of the LEDs are. Someone remind me, which is the row supposed to be high, or is the column supposed to be high? One of these ones you're supposed to make the voltage high, and the other one is low to get the LED to light. And then, as I think people are finding, when you're matrixing like this, it's difficult to light more than one LED at a time. So typically to create some pattern, you'd go through the whole matrix and test each LED individually and see if you need to light that one and do it. And that's the same as you would scan through a matrix on a keyboard in the input scenario. You'd be scanning, the microcontroller in my keyboard would be scanning continually across each key to see if it's been pressed. Because when you press a key, it may seem like it's fast, but from the microcontroller's perspective, it's very slow, you pushing down on the key and then releasing it again. So the keys on a keyboard get scanned, and then to light up a lot of different LEDs, you would want to scan that as well and iterate through all of those LEDs to get them to do something. Of course, how to do that in assembly is a challenge. Rows high, columns low. That's what Nick has said. Anyway, just so you know, like, all of the information is available. If you have a look on the books and references and links page, you can see a lot of good stuff. Let's go back to the stack before I get completely distracted. We're going to look at the how the stack works again. You may remember this concept that the stack is a very simple data structure in memory, which is there by default and kind of supported by the hardware. The reason it's supported by the hardware is that we have this SP stack pointer register, and the stack pointer register is designed to always point to the start of the last used element on the stack. And you know from Monday's lecture that the stack grows down. So if we push something onto the stack, we fill in this block of bytes. We push another thing onto the stack, we fill in that block of bytes. Another block of bytes, another block of bytes. Of course, well, not of course, but just so you know, not all data is contained in neat one-word packages. If we wanted to put 4 bytes of data on the stack, or 4 words of data on the stack, sorry, we can easily do that. We just have to write 4 times, because each writing operation can only do 1 word, and then move the stack pointer down to here. So the stack pointer is a register specifically used for maintaining this stack data structure in memory. And you remember that although we can use the store and litter operations to correctly maneuver our stack pointer, we've also got dedicated operations that can do it, push and pop, and we'll learn a little bit more about push and pop in a minute. And push and pop automatically know how to move the stack pointer as you're pushing things on top of the stack or at the bottom of the stack and popping them off again. Remember that SP is just a memory address. The stack is a normal part of memory. It's just stored at the top of your memory, your valid memory area, growing downwards, whereas your other memory tends to stay at the bottom and grow upwards. So hopefully they never get overlapped. And if they do get overlapped, we got bad stuff happening. Yeah, stack instructions. So this was sort of the manual way of dealing with the stack, and we went through this in a demo, but the first thing you would do is store a new value on the stack. Suppose our stack pointer is here. This is already filled in. We've got another word of empty space. We're going to store R2 in the value of SP minus 4. So we're actually going to store R2 starting down here. That gets filled in with R2. Next step, we have to update the stack pointer, sub SP SP4. And that means we move the stack pointer down there. So that's a push. The opposite way is a pop. We load whatever we had there, load R2 into R3, and then we add 4 to the stack pointer to move it back up. Pop. And that's push. And remember that you don't always have to pop. Sometimes you just read things off the stack without moving the stack pointer because you'd like the stack to still have everything there. Pop, even though we're not doing anything to erase the data when we pop, but we're still basically erasing it because the next time you push, you're going to overwrite it. You know, I can't remember if there's a typo. Someone that says there might be a typo in this code. I don't think so. Unless you find it. And here was push illustrated just as I was talking about filling in this location and moving the stack point down. And pop illustrated. We're reading that value off and moving the stack pointer back up. Now we get into this sort of stack-specific instructions. So there's a couple of this operation called load and store with write back, which can load or store a bit of data from memory with an offset, and then update the index register by that offset, either before or after you do the stack. So we're going to talk in more detail about this offset write back stuff. So pre-offset addressing. We've got a base address that we're writing, our memory address, RB. We have an offset, a number of bytes. What we do is change the base address, add the offset to the base address, and that gives us this offset memory cell, and we write into that memory cell or read from that memory cell, either store or load, and then update the register, the original base address register. So why would this be useful? Well, you might be, suppose you had to move onto the stack, push onto the stack a big thing that takes more than one register to store. It might take 4 registers. So you might want to do 4 pre-offset operations where you move stack pointer down, write something into the stack, move the stack pointer down, write something into the stack, move stack pointer down, write something into the stack, move stack pointer down, write something into the stack. So that it's a kind of set number of operations. You're saving yourself quite a few lines of assembly code by doing that. Particularly if it's in a loop, has to do it a lot. Post-offset addressing is that our memory cell for reading or writing is the same as the base address, and then after we've done our read or write, we change the base address in memory to the offset address. So this one, the pre-offset addressing, tends to have more to do with push, because when you're pushing, stack used up to there, stack pointer's pushing here. When we're pushing, we want it right into this area. So our stack pointer needs to be moved, so we can move it down and then right into that area. Pre-offset has more to do with pop, because suppose where our stack's used down to here, and we've got this value, we want to read that off, the stack pointer's putting here, we want to read that off, and then after we've done reading it off, we want to move our stack pointer up here. So first read, then move. Another example of these, you can do the push in one operation, stir R2 SP, comma -4 with the exclamation mark. And then we've got a pop This is the post-offset version, and you've got your offset as a sort of third parameter for the litter operation. Totally fine way to write to the stack. The other way we just did was a totally fine way of writing for the stack, to the stack. But then, as it turns out, this kind of movement of the stack pointer is so common, the pre-offset and post-offset changes with push and pop respectively. It's so common that we actually have specific ISA instructions called push and pop, which are specifically to do with writing to SP. But by contrast, you don't have to have SP here. You can have any other memory address in the world. R9, R4, any memory address. You could make up another stack in memory and use str R2 and litter R3 to that stack while continuing to have your SP stack fully set up and happy. But push and pop only work with the stack that SP points to. SP doesn't have anything special to know where that stack should be. You can set it up. You put a memory address in SP at the start of your program to define where that stack is, which is in the startup script. But it's a special memory address which is assumed to be used for a stack used during your program's operation. So push R2 and pop R3. These are exactly the same as this store R2 SP -4, exclamation mark, and litter R3 SP, 4. Now if you're following along from last lecture, you might recall that we had this idea that we have to store a bunch of registers on the stack at the start of a function. So maybe you'd like to have push LR, push R0, push R1, ... push a bunch of things and then pop a bunch of things at the end. We'll talk a bit about that in a minute, but this starts to look like it's going to get rather verbose. A lot of lines of code to do this. Don't worry, the ARM ISA has your back in this instance, because you can actually push and pop multiple registers. Mind blown. I know, it's just the exciting moments keep on coming in this lecture to do with the stack. Push and pop can take multiple registers. In fact, you can, in one line, in one instruction, push all of the relevant registers, all of the ones that are available to you, really, and in one line pop them all. And you can also have LR in that list. LR. LR. So push will put these all on the stack, and it will decrement SP by that amount, and then it will pop them all from the stack like that, like so. How's that work? That's got to be somehow some kind of crazy encoding to get this to work, right? It's quite simple, really. This is the push, the little push instruction. This one only works for the first 8 registers and LR. There's another one that the wide instruction can work with all of your non-special registers. Someone's asked what order will they pop. That's the one thing I always forget, but I know that if you have them in the same, they always push and pop in the same order, and they push and pop so that this works, right? If you've got something in R0 here, the same thing in R0 will be there. So I've forgotten what the specific order is of these operations. We'll find out in a minute. We'll do a test. Remind me to do a test with push and pop, so we find out what order they put onto the stack. Okay, so here's our push operation. Register list is a sequence of bits. So if this bit is set, that means it's going to push R0. If this bit is set, it's going to push R1. That's R2, R3, R4, R5, R6, R7. And then this one is just LR. So there's a space there between R7 and LR, not covered. In fact, there are more flexible versions of this that can work for any register as the base, not just SP. So push and pop are only for SP. These other instructions let you do the same operation essentially on some other stack that you've set with a different register. They have 5 letters in them, so the mnemonic for remembering them is a bit confusing, but this one is load multiple decrement before, load multiple increment after, store multiple decrement before, store multiple increment after. So the cool thing about these is that these ones load multiple increment after. These ones are our normal stack, descending stack. These ones can be used for an increasing stack. Or maybe I'm not right. I'll delete my comments. If we had an increasing stack where we were pointing to the last filled block and I want to push to that stack, I need to increment before and then store. Well, it doesn't give me that one. Maybe I'm confusing myself here. I'll look at the cheat sheet. So it felt like it was more positive stack. Store multiple increment after. Load multiple decrement before. Negative stack. Store multiple decrement before. Load multiple increment after. Well, that was my understanding, was that the other 2 of these would be what we use for our normal descending stack, negative stack, and the other 2 could be used for making an increasing stack if you want to. Maybe not a full stack, maybe it's the opposite configuration, where it's pointing to the last empty space. What would you do with multiple stacks, someone is asking. Well, it's a great point, but maybe your program might like to have a stack for functions to deal with, because normally the stack is very dedicated to the operations of a function. But you might want to have another stack for dealing with some general data, some kind of data structure of use to your program. So the stack is usually used to help functions to work. So it's like, I don't know, if you have I'm imagining a tractor has an engine, but the engine is required to make the tractor go. But then you might have another engine to do a job, right? So you need 2 engines. So your one engine is for the tractor and the other engine is for the crane or something that you're pulling. So in this case, if you have 2 stacks, one stack is required to make your program work because you need a stack to use functions. And the other stack might just be a data structure for storing data during your program. But the ISA doesn't tell you what to do with it. It's up to you to find use cases. More reading about the stack, and I encourage you to do this. Now we're going to get to the bit where I tell you, particularly Ben Eder, what a guy, great video. Functions and stack frames. This is the bit where I explain why stacks are necessary for functions. So, as you know, we talked a bit about this before. The calling convention makes suggestions about which registers a function should keep, what it should do with them, or which registers a function should look after and restore their value afterwards, and which registers can get thrown away, which registers could be input data for a function, and which registers could be output data for a function. So given that, it tends to be that whenever we use a function which has significant code in it, we do some stuff at the stack at the start and some stuff in the stack at the end to kind of prepare for the function to do its job and clean up afterwards. So we call these the prologue and epilogue of a function. The beginning of a function, the prologue, has got to do two things. Store on the stack any values in registers that need to be saved during the operation of that function, and that usually includes LR. If you have a function which calls another function, LR is going to get overwritten, so you need to push that on the stack. Very important. First thing you do. Secondly, you would also make room for temporary variables by decreasing the stack pointer. And this seems a little wacky, but sometimes we will just push empty space on the stack, essentially, just to have some room. And the reason we do that is that our functions that we call during the function will also use the stack, and we don't want them to overwrite our writing paper, our scribble paper. So we're making some room on the stack. Stack going down. My function stack pointer starts here and my function starts there. I pushed on LR and my registers, LR and the registers. And if I call another function, they're going to put on their LR and their registers. But I want this space to be my scribble paper for doing my work with local variables. So I'm going to claim it before I do anything else in my function. So by the time I'm done with the prologue, SP is down here, and this may just all be zeros or something else, but I've saved it as my space. So don't step on my space. At the end of the function, we're going to delete all of our temporary variables, so we re-increment the stack pointer up, and then restore all of the stored values that had to go back to where they go. And the last thing you do is make sure, well, two last things, make sure the return value is in the right place, and make sure that the stack pointer is where you left it, where you found it at the start of the function call. SP should go back to where you found it. Someone asking me a question, or is it another team? I can't see any any other things there. Ah, it's in a chat. It makes the same noise. I need a different noise per team so I know what's going on. So you can think of the stack as being a lot like a share house kitchen. I know a lot of you folks will live in share houses or shared apartments, and you have to have rules in the kitchen because we all know that even with the best of intentions, people have different approaches to using their kitchen. We need to have conventions about whether one is allowed to use things that one finds in the fridge, whether one should be cleaning up after themselves, whether one should be leaving all the dishes in a big pile for everyone to clean up on Saturday. Usually the rule is like, you don't touch other people's stuff and you clean up after yourself. That's sort of the basic kind of share house code. And that's basically what we're trying to do here with functions. Every function looks after its own stuff. Functions don't touch other functions' stuff. And each function cleans up after itself so that when that function is finished executing, the stack is back the way that it was when it started. Here's an example. A simple one. We're just pushing and popping off the our stored values. So we can assume that this function is taking 3 parameters in R0 to R2. So the first thing we might do is push those values on the stack and then push LR on the stack. And we could do those I think that works in one operation. I'll just make this. Don't tell me I'm wrong. push R0, R2, LR. Oh yeah, of course it works. I think I didn't write this slide originally. I think the person who wrote it didn't realize you could have LR stored there. I just edited some of these slides. Some of them are my original work, and some of them have been passed down over the years by successive COMP2300 lecturers. So we push our parameters onto the stack, so we have them kept safe. Push LR onto the stack. Then we do our stuff in our body. We don't know what this function does, but we do know that we need to leave a return value in R3. So in the last thing we do is, last bit of the function, mov R0, R3, so we're putting return value into the right place. R3 is a weird choice for a return value, but okay, you're allowed to choose that. Then we pop LR back into its location. So LR and matches that push. It was the last thing that was pushed, and now it's the first thing that's being popped. And we could pop back to R0 to R2. Rather than do that, we're just going to increment the stack pointer. So this is basically deleting R0 to R2 from the stack. Excuse me. I wonder if we all get that. Sometimes I don't get these things. I'd really like to remember what order the registers are pushed and popped on the stack. We might try it in a minute. I've got a little bit more theory to get through before we start doing these experiments. What I'm going to introduce you to is this concept, a stack frame. So whenever you run a function, it's got like my stuff on the stack. So a function's stuff on the stack is called a frame. And a frame typically has quite similar structure in between functions. So we might have our stack pointer might be up to here when we start our function. And then we do, similar to the previous slide, we push something onto the frame, push on some parameters, push on the return address. During the function call, we might have some other stuff we're doing. So this is all sort of the prologue. Saved resources, oh, that's part of the prologue as well. Those are things that might be in registers already that you have to save. And then our local stuff, prologue goes down to here. Our local variables are getting stored on the stack as well. At least we will allocate space for them if we need them. Then that's our function. So that's pretty simple. But what happens when you have some nested functions? Nested functions. Now here we've got LR and R0 on the same slide. What happens when we have these nested functions? Let's just have a think about it. The first function is going to push R0 and LR onto the frame. That's its frame. Second function now gets run, BL middle function. So SP is down here. Middle function is going to push its R0 and LR onto the frame. LR, R02, LR2. Okay. Middle, that's outer. And now SP is down here. Wow, I want to erase some things. I thought I had a button for erase, but I don't. I only have a button for make more mess. Now my inner function is going to run. The inner function doesn't use a stack frame. I guess it doesn't need to change any values, so it's not going to bother doing any of that. So then there's nothing for the inner function to do but bxlr. It blx's lr and we end up here. So then we pop off R0 and LR, stack pointer moves back up here. Essentially, this is erased. Once the stack pointer moves above it, it's erased. Then we bxlr, we end up back here. Pop R0 LR, that gets erased. Stack pointer moves back up here, and we're back where we started. So at the end of each function, they're tidying up their work behind them as they back away and just get ready to do the last thing, which is to return to their called address. So all of these frames kind of have a similar structure in memory, going down and going up as functions conclude. So here's some nested stack frames. Whew, there's a lot of stuff here. I guess there's a few more things we might have to do in each instance, but there's the start of our function. The outer function starts, it stores, pushes all the parameters, return address, call E saved resources, so registers that the call E is supposed to save. What are they? R4 to R something, right? I've forgotten. Is it R4 to R11? I think those are the registers that a function is supposed to not overwrite. Then it stores its local variables, and then it says, hey, I'd like to call another function. But I might have some values in R0 to R3 which I want to save, so I'll store those on the stack before I call my function. So I save the caller saved resources, save my own stuff, and start a new function. New stack frame, starting there. So this is stack frame 1, and this is stack frame 2. The new function, the middle function, stores its parameters, stores its return address, stores its call E saved resources, R4 to R11, stores its local variables, and then does some calculations and realizes, I'd like to call a function too. So this function saves its call E saved resources. The function saved its call E saved resources, called the function, and there was a third stack frame. This is starting to turn into a children's story, isn't it? Again, I have a small kid who likes to be read stories, so I start to go into a storyland tone sometimes, that's why. So the third function wanted to save its resources. The third function found it had to save its parameters, it had to save its return address, and it had to save its call E saved registers. Then it had some local variables to work on. The third function didn't need to call any more functions. So the stack frame ended there. So that was our third stack frame. And when the third stack frame, SP was down here, when the third function was done, it removed all of it restored the stack pointer to where it started and returned execution to the second function. And then when the second function was done, it returned the stack pointer to where it started and returned execution to the first function. And that function returned the stack pointer to where it started and returned execution to the main thread of execution. And everyone was very happy. So all of these little nested stack frames, 1, 2, 3, one after another. And you can see that, maybe you can imagine your program going down, and you might think, what if I run, this is running functions kind of within each other. So function 1 might go into function 2, which then calls function 3. But what if we have function 1 which just calls function 2 and 3 in sequence, not nested. Well, what would happen there is that we get down to here, function 2 runs, does its stuff. When function 2 has finished executing, we can be confident that the stack pointer is back where it started, over here, and the stack is cleaned up. And then function 3 will run, and instead of its frame being down here, its frame will start up here, if we're in sequence, not nested. Any questions about this, or someone got to have a question? This is weird stuff. I'll sip my coffee while I wait for a question to emerge. Who has a question for me? So you can see the SP is going to zip up and down the stack as the program executes, moving all the time. Totally fine. That's how the stack works. It's there to be used. We need to use it. There's more things we can do with our stack frame. I'll talk about this thing called the frame pointer a little bit later, on Monday probably. I should write that down. Talk about the frame pointer on Monday. I have a wild thing which is happening on Monday, which is I've got a free week of lectures. This never happens. I think we've done very well for time this year. We've been very efficient. And week 6 has often had like some kind of crazy catch-up session or something, but this year it seems like we don't have anything to do. So I'm just going to spend Monday doing only interesting demos, and if we need Thursday, we'll use it for something, and if we don't need it, I'll just give everyone an extra hour back to do their assignments. Someone's asking if sequential is better than full nesting. No, it's not. None of them is better than the other. Use as much of the stack as you want. You're not going to run out of stack space in this course, hopefully, unless you do. But yeah, it's just, I was just trying to say that in some scenarios, the stack will move in a different way than others. If you need to nest functions, you need to nest them. We're going to do a recursive example in a minute, which will certainly have nested functions. Next week, we'll look at a bit at how compilers generate stack frames. We'll try that. And I'd like to show you some recursion. You won't have to wait till lab 7. I'm going to do it right now in a minute. Someone think of a recursive function and tell me to do it. Recursive functions by request. So yeah, final things. These are all conventions. I've shown you here kind of the expected way to use the stack. The stack is set up within your microbits hardware, so it's there to be used by you. It's very useful. It's hard to do functions properly if you're not using the stack because you don't have these neat places to store stuff. Someone wants us Fibonacci. That's a classic, isn't it? We'll do Fibonacci. For bare metal assembly programming, you're the OS programmer, you're the compiler programmer, you're the library programmer, you're the applications programmer. You just have to make the convention for yourself. Okay, Fibonacci. How does Fibonacci work? Does anyone know what the Fibonacci sequence is? So, the Fibonacci sequence starts with 2 1s, and then you add, to make the next number in the sequence, you add the previous 2 together. So if I've got, this is one's going to be hard, it's going to take me ages. If I've got those previous ones, I need to add them together to get 2, and then I need to add those previous 2 together to get 3. Then I add these previous ones together to get 5. Then these previous ones together to get 8. Some of the previous 2 numbers. Okay, and so on and so forth. So I'm going to just map out my function here. I'm going to be calling Fibonacci with some number n, and it's going to be defined to be if, this is a comment, I'll fix the comments in a minute, if n equals 0, return 1. If n equals 1, return 1. Else, return Fibonacci n minus 1 plus Fibonacci n minus 2. This is not the easiest. I might ask for an easier one. We might do this one on Monday. What's an easier, because I have to do two recursions in this line. See what I mean? That makes it a little bit tricky to see how the stack works. I'll do this one on Monday. Definitely it's a good one to do, but how about just doing recursive multiplication? I'm not going to do sorting. I don't have a data structure to sort. Recursive multiplication. Or like factorial. That's probably easier. So the factorial function is going to be factorial n. This is it's in maths, like there's a n exclamation mark, and in maths that means 1 times 2 times 3 times 4 times ... times all the numbers until you get to n. This one's going to overflow our poor little 32-bit registers very quickly, but we don't have to worry about that today. So how's this one work? If n equals 1, I should have 2 equal sign there. Return 1, else return n times factorial n minus 1. So for all recursive functions, you've always got a base case, right? There's my base case. If n equals 1, return 1. And then I've got a recursive case, which is if n is anything more than 1, we do some work and then have a recursive call to the function, factorial n minus 1. I'm going to cut my other functions, don't need them. Don't need any of this stuff. I'm going to make my function down here at this label called factorial. I'm going to say parameter is in R0. I'm also going to say return value is in R0, so that's going to be tricky because we're using both R0 for a parameter and for a return value. So first things first, we'll assume we've got our number in there. Last things first, we move answer into LR, into R0. I don't know how we're going to do that. We're going to do a prologue. We're going to be calling another function, so we definitely have to push LR. And we're definitely going to have to pop it off at the end. Let's do our if then else. Compare R0 with 1. Okay. B, N, E, or B, Q, not recursive. I should do forgot my best if then else statements. I'll just hack through it, and if it's bad, you guys can tell me what to do. You folks, sorry. If it's not equal, we go to the recursive case. We're going to make that a label. if it is equal, we mov R0, 1. Oh, it already has 1 in it, so we don't really have to do anything, but there you go. I'll just say exit because it's 1. Okay. For if then else for the base case. R0 is already 1, nothing to do. Okay, now we've got our recursive case. So here's where we have difficulties, because what I want to say is this. Sub R0, R0, 1. Okay, and that puts n minus 1 in R0. Then I want to do another call for my recursive function. BL factorio. Proctorio? I'm lost. BL factorial. And then we add R0. But wait a minute, my R0 is now gone. I need to store my R0 somewhere. So I better do something to store my data so that it doesn't get clobbered by this call of factorial. That's going to put factorial n minus 1 in R0. What I better do is push R0 onto the stack. Okay, store R0 safely on the stack. Now after I've got my new factorial into R0, I'm going to pop off that value. I'm not going to pop it off into R0, I'm actually going to pop it into R1 because I need to keep what is in R0 happy. Pop n into R1. I should be saying store n safely on the stack. And then I will say add R0, or mult, sorry. Yep, so then set R0 equals factorial n minus 1 times n. And then exit the function. Don't have to do anything else. I think I've done it. Do you think it will work? Umul. What's umul do? Just so we're clear about our muls. Ooh, we could be doing unsigned 64-bit multiplication. Someone was suggesting in the chat, I shouldn't use mul, I should do 64-bit multiplication. Yeah, I'm not going to do that. That's too annoying. Just move my comment down there. And then up here, I'm just going to do a few tests, okay? Just so I know things are working. We'll test it with the base case to start with. So set up parameter for factorial, call function. Let's see if it works. Probably not. What have I done wrong? Now stop, listen, and look, Charles. Garbage following instruction, be any recursive case. I put a colon there for some reason. Garbage, that's what I've been writing. Make is very, or GCC is very unkind. They called my code garbage. They could just use a slightly more positive tone. Okay, we've got 1 in R0. We call our factorial function. Push LR, that seems good. Compare to 1. Be any recursive case. The base case is there. There's already a 1 in R0. We don't have to do anything. And we exit the function. Pop LR and go back to where we started. And we have the expected outcome. 1 is stored in R0. What if I do 3? Slightly harder. I could have just changed it in the register there. I might do that in a second. Move R0 3. So now what we have to do is, if you recall, 3 times 2 times 1. So it's going to push LR, compare to 1. It will find it wants to do the recursive case, store R0 safely on the stack, subtract 1 from R0, so now R0 is 2. Now do another factorial call, if my debugger can handle it. Uh-oh. That doesn't seem good. My debugger has just gone crazy. Did I press the wrong button? How odd. No, that doesn't seem good. I should post about it on Piazza. Huh. I'm just going to use the emulator because that's weird. I'm not using anything that can't be done in the emulator right now. Put R0, 3 in R0, go into factorial. I'm still on 3 here. Push LR, do the recursive case, push R0, sub R0, R0, 1, BL factorial. It doesn't work. Oh no. What have I done wrong? Something. That's very strange, isn't it? Well, just to be nice to my debugger, I wouldn't have expected you to have to do this. I'm just gonna make sure it knows where that function is. I haven't actually tried this, at least with a microbit. I haven't tried. I guess I wrote some recursive functions last year in assembly for something, but not very many. Oh, now it's happy. It knows what the function is, so I guess for the debugger's benefit, we should always use the .type directive so it doesn't get confused. It didn't used to require that, but I was using a different debugger. The last time I did this in seriousness was 2 years ago, so. Push LR, compare to 1. We've got 2 in R0 right now. We're going to push down to the stack, subtract 1. Now we go and do the base case. So what's our situation now? We've actually got 3 stored on the stack, 2 stored on the stack, and 1 in R0. And we're going to recursively pop off those numbers from the stack, the 2 and the 3, and then multiply them by 1. So we will pop back to here. We're going to pop 2 into R1. There it is. And now we multiply we get 2 in R0. Exit function, we're going to pop 3 into R1. That did it. There's the 3 in R1. Multiply them together, we should get 6. Pop LR, BXLR out of it, and we're back in main. It works. What if we do something slightly more complicated? Or I'll go in the variables area. You can change variables here, so that's fun. I'm going to put OX 8. Put a breakpoint there. Oh, it still had 3. Oh well. Oh well. Couldn't get it to work. We'll start with 8 in R0. It's going to have to do a lot more winding down. I'm just clicking through quickly so you can see it counting down. Now at 1, we can do the base case. So we should have 1, 2, 3, 4, 5, 6, 7, 8 all stored in the stack, and my function is going to pop them off and multiply them recursively now. And you can see that number is getting very big very quickly. And that's the end of my story. One more test. What about if I had 0 here? What's the factorial of 0? It's defined. BL factorial. Doesn't know what to do and starts at f. And actually it got broken. It ended up in the default handler. So I think we ran out of stack space that time, actually. So I would need to do another. I should check for 0. Also check for 0. Should return 1. That's the definition of factorial 0. Someone says try with 6. All right. I'll just press start and see what the breakpoint says. It gets the breakpoint and I've got this big number, 720. Is that 6 factorial? 6 times 5 times 4 times 3 times 2 times 1, 720. It works. Our first recursive function in assembly. And you can see that this recursive function completely relies on the stack, which is a recursive data structure, right? And every time the function has to do something, it pushes some information about what it has to do onto the stack. And then when it does the work in this kind of tail recursion thing, it pops them off and multiplies them by each other. Now that's all that I wanted to do today. 10:15. So I'm going to wish you good luck over the weekend. For those who still have their labs to do their design proposal discussions with the tutor, enjoy that. It's a great chance to have a chat with your tutor about what you want to do in the assignment. Please get started with the assignment over the weekend if you have some time, even to do a little sketch in assembly of your idea. See how hard it's going to be and correct early. And if you have any issues with the assignment at all, please ask on Piazza. We're here to help you. We may not get to answering them until Monday, but we will still be able to offer you good help if you're asking early. That is the start of the weekend and the start of next week, rather than later towards the end of the week, where we won't have time to address questions before the deadline of the assignment. So I might prepare to go and do my next thing. Have a great Thursday and Friday and weekend, and I will catch you folks on Monday for a big demo and worked example time. I promise I'll do factorial recursion with 2 recursive calls on Monday as well. So until next time, catch you later.